So I'm Ofir Lindenbaum, and I'm currently at Yale University. And I'm going to talk about feature selection using neural networks. So to start, I guess you all probably know that machine learning has done a great progress in the last few years. And most notably in three domains, these methods have, specifically deep learning methods, have been able to close the performance gap between what we as humans can attain in terms of the error rate and compared to these machine learning-based algorithms. And the three specific domains are in vision, natural language processing, and in audio processing. And there is one thing that is common for all of these domains is that there is some underlying structure that is used to design the deep learning algorithms. Specifically in the images, we're using the spatial information. In language, we're using contextual information that is inherent to sentences or documents. And in audio, we're using the temporal information. Perhaps, slightly in contrast to this, when we're using empirical observations from natural science, like what happens in biology or in medicine, we often have some latent space which could describe, a lot of genes, and then we have some measurement device which creates our observation space, and this gives us a matrix of observation which has different measurements with different variables. And then we might have or not have a label space. And if we have a label space, we will want to try to make predictions. For example, if a patient is healthy or infected based on these matrices. So the goal here would be, given observations from this joint distribution, we want to learn a predictive function. I want to point out that there's several key differences between the three structured domains that I've listed in the previous slide into a lot of these unstructured data, and that is when we're using empirical observations from natural science, we often have very high dimensional data sets which can have more variables than samples, which is a regime which is very hard to avoid overfitting. We might have nuisance variables. Those are variables with no predictive power. Again, this is not typical to images. Usually we take images of the information. We may have inaccuracies, which are due to the measurement device. So the measurement device can create some deformation. There could be noise or missing values. And a lot of the times the labels are imbalanced. So we have perhaps one class is much more present than the other class. In this talk, I'll focus on the first problem, which is the dimensionality of the data and the nuisance variables. And I'll focus on the problem of feature selection, which deals with identifying a subset of informative features while learning a predictive function. And I'll try to motivate this using a very simple example. So let's assume we're given this set of patients with different genes and clinical variables, and we want to predict the survival time of each patient. So you can see that here, as opposed to images, the variables are consistent across the different patients, as opposed to specific pixels and images are not representing the same thing across the different samples. And perhaps in some of the cases here, we might have a lot of variables, way more than the number of samples. So what we're going to try to do is we're going to try to identify the informative features and learn a predictive function to predict the target in this case, which is the survival time of the patient. So let's try to formalize this task. Before that, I want to stress some of the advantages of doing feature selection. So like I said, it allows us to handle very high dimensional data sets, and it can improve generalization in the sense of reducing overfitting. It can reduce the computational costs both in the training phase and also in inference, because at inference we're going to only have a few variables, but also during training we might be able to lose gradients of some of the non-informative variables. And last but very important, we get some interpretability in the sense that we can identify the informative variables, and then physicians can only measure those variables to make predictions in the future. So I see there's something in the chat.
Yeah, if there is questions, I will raise it from the chat. No worries, Ofir, you can continue.
All right, thanks. So let's try to formalize this. Let's try to have a more formal definition of the task. So we are given observation from this perhaps unknown joint distribution of x and y, the observation space and label space, and some integer number k. And we want to learn a predictive function from x sub s to y, such that x sub s is x as the variable x restricted to the set of features which is selected by this indicator vector s, which is a vector of 0, 1s, that is 1 for a variable that's going to be selected, and it's going to be 0 for a variable that's not selected. So we can have a constraint on this. We want to have this vector s with an L0 norm not greater than k. So we don't want to have more than k active coefficients in that vector. So effectively selecting no more than k variables in this case. We can do this by trying to minimize the risk. That is the comparing the loss, some loss function between the predictive function and the target variable, with a constraint that the L0 norm of the indicator vector s is not greater than k. So this constraint would force our model to select no more than k variables when trying to identify the function f from some class of hypothesis functions. Alternatively, under certain choices of a loss function, we can approximate this risk in using a mutual information perspective. And we can, instead of minimizing the risk, we can try to maximize the mutual information between the vector of selected variables in x using this indicated vector s and the target variable y, constrained again to not having more than k active coefficients in the vector s. Right, so this is an
yeah. There is a question here. How do you select the v, or how do you select the k vector, or sorry, how do you select the k variable?
So I'll get to that later. I guess at this point this is not really presenting the method. It's kind of trying to formalize the problem. Let's assume at this point that this is inherent to the problem, that I want to identify exactly k features for some reason. I want to identify 100 features. Perhaps later I'll show how I can try to evaluate what is the optimal k. But at this point, let's assume that I just want to select a fixed number of variables. Okay, so one way to approach feature selection, assuming that the model that creates our target variable is linear, which could be created by this illustration where we have the observation matrix X, again with n measurements and d variables, that's multiplied by an unknown set of coefficients beta star with some additive noise. And this beta star has a subset which is active, indicated here in red, and a subset which is not active. And we want to use X and Y to identify beta star, and specifically identify the subset of active variables in this case, subset of active coefficients. So we can do this by using an empirical surrogate of that risk that I presented, by trying to minimize the empirical regularized risk in this case. So that is, we'll have an empirical estimate of the expectation. That's the left part of this term. And by choosing some loss function, this loss function could be the mean square error if we're doing regression. It could be the logistic loss if we're doing classification. And on the right part, we're going to have a regularization term or penalty applied to the vector of coefficients. And we're going to have a regularization parameter that's going to control the amount of feature selection or the amount of sparsity that we're going to impose on the unknown vector beta. There's several ways to impose such regularizations or penalty. One way is using the L0 norm, which seems very natural, but this becomes computationally intractable if we have very high dimensional observation spaces. Alternatively, several authors propose to do hard thresholding instead of using L0, or actually this last work, Milk, does solve the L0 for even 100 features using tricks from linear programming. And alternatively, a lot of people use the L1, which is known as the lasso, and also induces sparsity and is cast as a convex problem. So it enjoys very fast optimization schemes and has several extensions like the train lasso, iterative support detection, IRLS, or IRL1, which I've listed below. There's several extensions of this idea to nonlinear functions. I've listed a few of them. I believe the list is much longer. I've tried to separate them into three families of extensions. One is generalized linear models, which take the idea from Lasso, but just generalize the linear function to specific family of nonlinear functions. Kernel methods, which gain the linearity using a kernel function, but the caveat here is that the nonlinearity is feature-wise and does not take into account nonlinearities of combinations of features. And neural network methods, which I cited two examples, and I've talked about more in the next slide. So Li et al. And Feng et al. Proposed to do feature selection using a neural network, using an idea which was very analogous to Lasso. So basically using an L1 regularized neural network. If you're not familiar with neural network training, the idea is you're applying a composition of matrix multiplication plus addition of a bias. Then you apply some nonlinear function, which is here denoted as sigma. This is what's called an activation function. Could be tanh, ReLU, or sigmoid, or any other activation function that you want to use. And then you want to minimize some pre-designed loss. In this case, they're using the empirical risk of some loss, which is either MS mean square error for regression, or logistic loss, or cross entropy for classification, plus a regularization term, which is L1 applied to the weights of the first layer of the neural network. So this can induce sparsity and actually do feature selection if it will select only a few variables in the input layer. The problem with this approach is, first of all, if you have very high dimensional data sets, it saturates when you reach the number of features as the number of samples. So if, for instance, you only have 100 samples, you can't fit this model for using more than 100 features. It does not perform well with correlated features. It requires thresholding throughout the training. So it doesn't induce sparsity by itself. You have to do gradient descent and then balance it with some thresholding. And from my experience, this is very difficult. And I think the last point is perhaps unique for deep neural network, and the biggest caveat is this is what the authors of these papers state, it's not effective for deep networks. So this works for shallow networks, but it doesn't work for deep networks because it's very hard to balance the gradients of this first layer, the gradient that comes from the regularization, and the gradient of the deep networks that come from the composition of multiple layers. And so we wanted to come up with an alternative for this approach. And that brings me to our work that I was going to describe here. I'm actually going to describe two work. The first was presented in ICML, which is a result of a collaboration with Yutaro Yamada, Sahana Gaban, and Yuval Kluger. And then I'll describe an extension of this idea to unsupervised learning, which is under review currently and appears in arXiv, and is a result of a collaboration with Uli Shacham, Jonathan Swirsky, Erez Peterforn, and Yuval Kluger. And I'll start with presenting the key part of the idea. So the idea is we want to introduce Bernoulli random variables through the input layer of the neural network. And each Bernoulli random variable can take values 0, 1. So 1 with probability pi d and 0 with probability 1 minus pi d. And the one nice property of this random variable b, when bd, when placed into a vector, so if I have capital D of those, then the L0 norm of this random vector by expectation is nothing more than the sum of the Bernoulli parameters, right? The definition of this expectation is just 1 times the probability of certain variable being 1 plus the next variable, and so on and so on. So this just boils down to being the sum of the Bernoulli parameters. And we will use this by incorporating this L0 into a gradient descent optimization. So we're going to avoid having L0 and gradient descent optimization by using this expectation of a random vector.
There are two questions. So one was, let me just find it. It's I think about 2-3 slides earlier. The Lasso regularization. Yeah?
I can see them, yeah. So the Lasso regularization is what induces the feature selection. Yeah, in Lasso, or in the neural network, the L1 regularization induces sparsity by shrinking the coefficients, and then when you apply thresholding, they're just being zeroed out. So that's what happens in Lasso in the L1 neural network. And then there's a question, is this similar to dropout? You're talking about here what I'm just starting to present, or previous slides?
I think about this slide right now.
So, okay, so I haven't gotten to the method. It is going to be similar to probabilistic dropout or variational based dropout. So in general, when you do dropout, if people are not familiar, you just randomly throw away weights throughout training. Here, we're going to actually learn the parameters of these kind of dropouts. So I'll formalize how we're going to learn them later, but it's related. Looks similar to attention layer, but yes, this might be similar to attention layer. Okay, so yeah, feel free to continue with questions. I have the chat open. Thanks. So we're now going to introduce these gates to the input layer. And the idea is that these Bernoulli random variables are open. So if they're open, the input variable propagates to the deep neural network. And if they're closed, if the variable takes value of 0, then the variable does not propagate. But I guess, perhaps different from dropout, we're going to do this at each iteration, and we're going to learn the parameters of the Bernoulli random variables throughout training. And we're going to identify which variables are more informative and which are not by, learning these parameters, these pi parameters, simultaneously to learning the parameters of the neural network. Yes. Okay. So, all right. So our first contribution is that we've wanted to justify this sort of probabilistic formulation to the problem of feature selection. And here, what we did is we used the following two assumptions. So assume there is, so I have a data set, and given that data set, I'm assuming that there's some subset of the variables, which I'll denote by S star, and that has no more than K. So it has exactly K variables in this subset. And each variable in that subset has some mutual information with the target that I'm trying to predict. So I have a subset of variables, they're all informative. And assumption 2 is saying that all other variables are not informative. So they're just basically nuisance variables, they're not helping me with the predictions. So if these two assumptions hold, then we show that the two constrained optimizations, maximizations, are equivalent. Essentially, the first maximization is a probabilistic maximization by constraining the L0 norm of the Bernoulli vector. And the second one is the deterministic maximization of this indicator vector S. And what this proposition is implying is that if these two assumptions hold, then our Bernoulli gates would place all of their mass on the informative variables, and they will converge to basically deterministic gates. So they will start out as being probabilistic, but their pi will be essentially 0, 1, not only their values. Okay, so I see that there's some questions. How do we choose which neurons to kill? All right, so I in the next slide, I'll explain how we introduce these gates into a loss function. And then by optimizing this loss function, the optimization will select which neurons to kill. If they are redundant, yeah. Sorry, there's another question.
Yeah, that's a good question. Instead of writing in the chat.
Yeah.
So you're turning off individual inputs or entire channels? Because I'm thinking like, how are you going to then modify the network so that it's actually slimmer?
So
yeah, thinking about a 2D picture, how are you going to erase like one pixel?
So yeah, so you're thinking of a pixel, just that pixel, once it's zeroed out, it no longer propagates to the neural network. So all the weights from that neuron, and
are we trying to slim the network? Because it won't be enough to just zero out a pixel. I have to zero out an entire channel to make the network smaller. And a follow-up question, or maybe more general, how is this in relation to other pruning methods?
So yeah, so this will zero out that neuron for the rest of the training, essentially. And we're not necessarily trying to compress the network, though we're gaining that. We're trying to, at the end of the training, look at the neurons and see which were zeroed out and which were not. How does this compare to other pruning methods? So again, pruning methods are focusing on compression of the full deep neural network. We're just trying to, if you want, sparsify the first layer. But if you use our technology to sparsify the full neural network, then in my experience, it outperforms just, norm-based pruning methods. And it does that, throughout the training. So you gain by losing, you reduce the flops throughout training because you sparsify as the gradients, as the training procedure, during the training procedure. Does this answer your question?
I'll continue following. Thanks.
All right, cool. So there's a next question. What if the variables are redundant? I think this is the question. So, here in terms of this proposition, we're not proving anything about correlated features. In practice, I'll show examples when we deal with correlated features.
There's another question, follow-up question by Narishima. Do we kill neurons during testing?
Yeah, so again, this is far ahead. I haven't described the training procedure. I'll get to the training procedure and then I'll describe the testing procedure. But yes, we are gonna.
We're so many people here and limited time, I will ask everybody, keep your questions. Let us run a bit through the lecture. Maybe some of the questions will be answered. And let's look in about 20 minutes. If there will be questions, we could raise them on the chat or with audio. Is this okay, Ofir? So we can start.
I have a break point in like 15 minutes, which is
perfect.
Great place for questions.
So questions in 15 minutes.
Cool. All right. So if we want to incorporate this into a risk minimization, which we're going to use for neural network, we can just multiply the input variables with those Bernoulli gates, add a regularization term, which is the L0 of this Bernoulli vector, and then take the expectation over this Bernoulli random vector, which again boils down to the sum of Bernoulli parameters. And that's why we can use this in gradient descent. So the right part is just parametric, it's just a sum of numbers. The left part is going to be estimated using Monte Carlo sampling, like it's estimated in standard neural network training, except we have this randomness in B. The problem with this idea is that due to this discrete nature of the Bernoulli random variables, we see this high variance in the loss function, throughout gradient steps. So we're going to take gradient step, we draw from these Bernoulli variables, and we see this huge variance in the loss. So the loss is very unsmooth, if you want. So to solve this, luckily, several authors have proposed continuous relaxations for discrete random variables. So on the left, I'm showing a Bernoulli random variable. On the right, I'm showing the distribution of a relaxed random variable, if you want. And the past work, there's Madison and Zhang, separate work, but similar ideas, propose the concrete distribution, which has a nice name. It's a combination of the word continuous and discrete, and is based on the logistic distribution. And then the hard concrete, which is use this distribution for model compression. But we saw that this distribution is also not suitable for the task of feature selection, again, because of this high variance of the gradient estimates. So we've proposed an alternative relaxation for Bernoulli distributions, which is slightly simpler. It's based on a Gaussian distribution. It's a mean shifted truncated Gaussian variable. So it's restricted to 0, 1. And on the top left, I'm showing so we have a Gaussian. We apply this function. On the bottom right, left, I'm showing the truncated function, and on the right, I'm showing the resulting distribution. And we're going to use this to multiply the input variables, and we're going to basically learn the means of these Gaussians, which will shift us to the left if the variable is not informative, and if it's informative, they will shift us to the right. So let's see an example. If mu is very negative, then this gate is deterministically closed. If mu is half, then it looks like a fair Bernoulli distribution. And if mu is something like 2, then it is almost a deterministically open gate. And now I can, fully describe our procedure. So our procedure in training is we draw from these Gaussian random variables, and we apply this hard thresholding, and then we compute the loss using Monte Carlo sampling on the Bernoulli variables. And on the right, we have the regularization parameter, which is just based on the error function of the Gaussian. And then we just take gradient steps to update theta and gradient steps to update mu, which controls the feature selection if you want. At inference, after we've finished training, after the losses converge, we use only the variables that have active Bernoulli, so have some probability of being active. So if the z, the deterministic version of z is non-zero, greater than 0, and we can use that, as the output for the set of variables that we were looking for. If we are practitioners such as biologists or medical doctors looking to identify sets of variables to have some predictive power. And in general, we can just feed in these variables, any new sample by just zeroing out the features of the non-active gates, because they're not going to propagate throughout our trained network. So let's illustrate the performance of this method using just a simple linear regression example. Again, this is the model for generating the samples, the x and y, and we're trying to predict this vector of unknown coefficients beta star. I'm using a very small example in this case for this illustration. I have 10 variables and only 8 measurements. So it's a very tiny example. And this problem is underdetermined. So if you just do linear regression, you can overfit because you have more variables and samples. But because there's sparsity, so only 3 variables are active, you can try to induce sparsity using our regularization to identify the correct active features in this case. On the left, I'm plotting the probabilities of each gate being active at initialization. So you can see that all gates are initialized with probability around 0.7. And then after only a few epochs, the gates that correspond to the informative features converge to probability 1 of being active. And vice versa, the non-informative variables, the gates corresponding to the non-informative variables converge to probability of 0 being active. On the right, you can see the 2 parts of the loss, the mean square error and the regularization term, converging to exactly 3 in this case, which is the sum of probabilities of the active variables in this case. Next, to see if this is really beneficial in linear regression, we fix the number of variables, we fix the sparsity, and we evaluate performance for different number of observations. We evaluate performance by applying 200 simulations and just quantifying the amount of success that our algorithm does in recovering the true support or the true active coefficients in this linear regression model. And you can see that our method in black outperforms the lasso in the sense that it requires much less samples. It also outperforms our method but using the concrete distribution, hard concrete distribution. And it also outperforms our model that removes the probabilistic parts. So just staying with this our regularization term, but reducing the injected noise essentially. Next, I wanted to have like a visual example to just try to illustrate our method on images, although I'm not recommending to do feature selection on images because of what I said in the first slide, which is, typically in images, pixels change from one sample to another. On MNIST, they're mostly centered, so I could select two classes in this case, 3s and 8s, and try to classify those two classes. And I'm trying to identify informative features to separate these two classes. In this case, I'm tuning the method to only select 7 features. And you can see that the method is selecting somewhat informative features in the sense that they're mostly active in examples of 8, and they're mostly non-active for examples of 3. So in this example, we can reach 94% accuracy in this binary classification. If we do the same thing using the hard concrete distribution, we see less informative features selected and also a larger variance between different runs. So the 2 rows just are 2 different runs of our method. Yes, there was a question?
In this context, features is a specific pixel in the image. This is you're running fully connected, so this isn't a convolutional neural network.
No convolution, correct.
All right, thanks.
Right, in the next example, we took a baseline, a benchmark data set for feature selection. It's called Madelon. It's a binary classification data set. It has 5 informative features, which are binary classes placed on this hypercube. You can think of this as a extension of the XOR problem. And we have 495 nuisance variables. And in this case, we're using less measurements than features. So we have only 450 measurements and 500 features. So it's a slightly challenging regime for neural networks. And we're going to try to train the neural network to see if it can identify the 5 informative features, which in this case we know. We have a ground truth that they are correct. And if the predictive power of the network is going to be good compared to other baselines. So we train our model and we compare it to the L1 neural networks, linear models, and some strong tree-based models. And you can see on the left bar plot that we attain higher classification accuracy in this case. And on the right, you can see that we attain better feature selection capabilities. In this case, we're evaluating precision recall, not of the classification, but of if we identified the 5 correct features. So this is precision recall in the sense of identifying those features. You can also see that the SDG distribution, the Gaussian distribution, is doing much better than the hard concrete distribution and is performing with less variance compared to that distribution. The next example is very similar, except instead of doing a classification, we're doing regression. But same setting, we have 5 informative features created by this nonlinear function. And we have the same number of features as before in samples. And you can see that the mean square error here, is outperforms other baselines, and also in terms of the predictive power of the informative features. Next, we've compared to several benchmark data sets for different levels of selected features, and we demonstrated that we can dramatically compress the feature size while attaining very high accuracy. So these accuracies that we reach at these plateaus are comparable to the accuracies that you reach with the full neural network trained on all of the features in these examples. So you can see in the table on top the dimensions and the number of sample size. So again, this is a question about what is the meaning of feature selection, F1 for regression. So let me again explain that F1 for both of this classification F1 and regression F1 is not in terms of the predictive, but in terms of the ability to identify the correct features. So that is, if I have 5 true features and all the rest of non-informative features, and then I'm looking at the selected features, perhaps I'm selecting 10 features, then I'm looking at the intersection between the selected features and the correct features, in quantifying precision recall in that sense, right? So perfect precision recall would be if my method is selecting exactly the 5 informative features and zeroing out all the rest.
Okay, I understand. You're treating the feature selection as the problem itself, as a classification problem.
Exactly, exactly. Thanks.
If we have time for questions now, Ofir, there is one from YouTube and another one from Mike from earlier.
Yeah, so this is a good question.
So Mike is asking, is this theorem somehow related to the theorem in the reinforcement learning field, stating that there is always deterministic policy maximizing the total reward under some conditional?
I'll be honest, I'm not very familiar with that theorem. I'll have to look up.
And Marius on YouTube is asking regarding the example at page 22, does the proposed neural net also outperform if K is differently chosen? 22.
Okay, so in this case, it's a good question. I actually skipped the answer from before that. I had to answer. So yeah, in these examples, I've selected K using a cross-validation procedure. So I basically have my samples, my training samples, which is this size. I leave 10% of it. So I even decrease the size by 10%. I use that as validation. I vary the K parameter, and I select the K that performs best on the validation. And then I use that for unseen samples. So these performances are unseen samples. In this case, I can generate as many as I want because this is artificial. And it was tuned by a 10% validation left out of this training size. There's also a question if I try data sets with more samples than features. So yeah, actually in these tables, there are some cases with more samples than features. And I've also tried other examples of that sort. Our model works for that cases. I have to say two things. It's beneficial in that case if you really want to identify the relevant features. If that's not your primary goal, then training a neural network without this would probably do the same in terms of the performance because it's less prone to do overfitting. However, you are gaining in terms of training speed and you're compressing your model. So, okay, so I'll just go to the last example, which is my motivating example. We use something called a meta-brick data set. And here we're trying to predict survival time of actual patients. We have 2,000 patients, and we've compared our model to a strong neural network-based model called DeepSurv, random survival forest, and Cox lasso and Cox based on hard concrete. And these models are evaluated with something called the C-index, and we attain a higher C-index by selecting much fewer features than the other models. And also you can see that comparing our model average over 20 runs, we have a very small standard deviation in this case. So this kind of summarizes my first part. And Peter, tell me how much time I have left. I wanted to also talk about unsupervised.
So basically we're supposed to have left half hour, but it's more dependent on you. Usually most of the audience likes to stay as long as you're able to teach.
Yeah, so I'll be happy to talk about unsupervised, but I guess this is a good time for additional questions because I'm going to switch gears to unsupervised learning.
I'm also posting on YouTube now that you have more questions because it's a bit in delay, the stream there. We have like between 10 to 15 people watching usually there now.
Okay, so I see there's another question I didn't address. Why does SCG perform better in the nonlinear case? I'm not sure if he, I'm not sure. Again, he's asking, why is the STG performing better than nonlinear case? Why is it performing better than other models, or why is it performing better than?
So Shalef corrected, I think she says I
Oh,
meant regression than classification.
okay. That's a good question. I think it's not about why. So I think it's more about why are these other models doing so poorly in this regression example compared to, here they're doing much more comparable, I think. For me, this is an easier problem. I think this is an easier problem because there's much more, okay, that might also explain our performance. There's much more mutual information between the individual variables and the target. In this example, you really have to identify the combination of variables. So I think that's why it was easier for our method. But perhaps there are other reasons that I relate to why other models are not doing so well. All right, so about random forest, it's a good question.
If we could
Random
just read out
forest,
the question first, because some people don't see this.
Yeah, sorry. So Tomer is asking, the previous slide showed the comparison to random forests, where the features are selected by their feature importance, question mark. So here I'm using actually 3 tree-based models. So extremely randomized trees, random forest, and XGBoost. I have to say all of these models are very good in avoiding overfitting when you have nuisance variables and less samples than variables. So in a lot of the cases, these models are good, but the thing that they're not so good at is at really identifying the actual relevant features, because they're going to do good, but they're not going to, they're looking at their feature importance is not going to always tell you which are the informative features. So what Tomer is asking, how did I train this? So I trained the random forest models. I sorted the features based on the feature importance. And then I trained an additional random forest model based on the selected features. So I kind of improved the performance of those models by retraining them. So it's a, perhaps more complicated procedure. But I guess that I want to stress the weakness of these models is that they perform well, but they do not, the feature importance is not always, a good indications of the actual informative features. And you can see that by the F1 score, which is, much less, good than in our model. All right, so have you tried select feature based on SHAP values given some train models from your task? So he's asking, have I tried to train a model and then select the variables based on methods that try to explain, the neural network models, or explain the first layer or deep layers. And, these models are very good for identifying informative features if the model has been trained properly. And I believe, and also from my experience, if the model is not trained properly, and that's going to be the case if you have much more variables than samples, and then the explanation is going to be flawed because your model is basically overfitting. So that's the caveat of doing this post-training procedure. Have you compared your method to classical dimensionality reduction algorithms like PCA? I want to stress that this is to distinguish dimensionality reduction from feature selection. Dimensionality reduction is actually doing feature extraction. It's taking a combination of input features to reduce the dimension. And we are actually wanting to subset the input variables to allow interpretability. So if we do PCA and then we just throw out some of the principal components, then we can't say anything to the, biologists, these genes are important or other genes are important. They're just principal components. They're not variables anymore.
I've got a question.
Yeah.
It might be a bit nitpicky, but in the data set where you have 495 like distracting dimensions, what would happen if some of those are linear combinations of the 5?
That's a great question.
It would probably
I
have
wish. Yeah,
yeah,
continue, sorry.
It would just be hard to define what's spurless, like what's necessary, what's not. They're all kind of like equally necessary.
Yeah, so that's a great question. I actually left a slide out of us doing it, so I can show it in the end. So there is a more challenging variant of the Madelon dataset, which is exactly what you're saying. It has 5 informative features, and then it has 15 features which are random linear combinations of the original 5 features. And then you have basically 20 informative features, and the rest are just noisy features, and you're trying to train the model. So I'll show in this additional slide that I'll pull up the result that we got.
Thanks.
I think we stopped at Tomer's question, was it? The feature importance there is a permutation or by mean difference in random forest?
The feature important there is by permutation. Or feature importance is providing by tree-based models are provide some feature importance. I don't want to go into
the standard implementation of in random forest is not the permutation variance for feature importance. So it's the second option is slower, but it's more indicative into the feature importance of the features.
Oh, so you're asking which option did I use? So I used the
Yes.
standard option.
Okay, thank you.
Thanks.
We have a question from YouTube. Again, Marius is asking on page 24. I wonder how much the proposed model performance improved over the unpruned one, also for some of the compared models.
So are you asking about neural network or about the tree-based models?
Not clear what he's asking, but his answer for this question will be a bit in delay to us because he's
okay, about the neural network, I guess
yeah.
we have here, I haven't pointed this out, but this is a neural network with no feature selection. So this is exactly the same architecture, and you can see it's doing not bad, right? It's classifying. The tree-based are doing better, but it's slightly overfitting. And same goes for this regression example. The neural network is doing some job, but it's overfitting. And this is the same architecture, capable of learning this function, but overfitting due to this, sample size regime. If you set K to 5, would your method identify the 5 informative features? So this is quantified by the F1. In this example, we can see that our model precisely identified the 5 informative features. In this example, we're not always doing that. You can see by the right that the F1 is not precise. But like I said, this problem is more challenging because there's no mutual information between individual variables and the target. You have to find the combination. When you train the tree algorithms with n most important features, how n was picked, I mean, the result might be very different for different n's. So I for all of these models, I did the same procedure. I had a validation set of the same size. I evaluated the, if the model has a regularization parameter, then I, varied a lot of regularization parameters, and I picked the one or the number of selected features which had the peak performance on the validation set, and then I used that for testing. So it's exactly the same thing I'm doing for our method. Because you show the result when F1 is the best, what was the K value at the time? Well, it actually is not a single, because these are average over 100 simulations. I don't have one value of K selected, but I have different variables for different instantiations. But I can say that for our method and for the tree-based method, they were pretty close to the true number. So they were mostly relatively close to 5. So they could be 5, 4, 6, etc. But most of the cases were 5. Your method seems similar to variational dropout applied only to the first layer. Do I miss anything? So yes, there are several ideas for variational dropout. This hard concrete distribution that I'm comparing to is used for variational dropout. Our model is different because it's using a Gaussian-based distribution, and importantly, this is what allows us to do feature selection, because our distribution has much smaller variance when we compute the gradient estimate, and that's important when you do feature selection, and perhaps it's less important when you do model compression. And when you do model compression, perhaps you can train 100 models and get 100 different compressions, but they can reach the same performance or similar performance. When you're doing feature selection, you really want to select the same features over and over again. So having a large variance in the selected feature is a very bad property in terms of feature selection. So that's why we use this different distribution. Are you using early stopping? I'm not using early stopping, I guess. But it could improve the performance in this case, but I'm not using early stopping. For our model, for the deep neural network, I am tuning the learning rate and everything using this, and the number of epochs using this validation set. Okay, so let's switch gear to unsupervised learning. So in unsupervised learning, we're given a data set, we don't have label information, and we want to infer something about the structure of the data. It could be clustering. That is, we want to identify groups of samples that are somewhat similar within. So the samples within each group are somewhat similar. Or we might want to do manifold learning. That is, we want to take high-dimensional observations and embed them in a low-dimensional space that coherently represent these higher dimensional observations. And both of these tasks, perhaps this is not something very discussed in the literature, but both of these tasks, if you want to do clustering or if you want to do manifold learning, your performance would deteriorate if you have nuisance variables. So, on classical examples where everything is clear, on images, then I don't have problem. But if I have 10,000 genes and a lot of the genes are just noise, then the structure that is hidden in this tens of thousands of variables could be masked by these nuisance variables. And to illustrate this, I'm applying spectral clustering, which is a well-known clustering procedure. And on the left, you can see the performance for no nuisance variables. Then once I add a noisy variable, you can see that the clustering accuracy deteriorates, and then with 2, it again deteriorates. And the same phenomenon applies for in dimensionality reduction method. ISOMAP, you can see for no nuisance variable, it can provide a 2-dimensional description of this original Swiss roll. And as I add nuisance variable, this our structure, our 2-dimensional structure is deformed until even in 2 variables, we get this overlap between samples. We really are destroying the structure that we're learning. So that motivates the use of feature selection, even in unsupervised learning. I actually stress that it's even more important in unsupervised learning, because in supervised learning, if you have enough samples, then your model can do well with no feature selection. And to kind of explain our method, let's first describe the graph Laplacian, which is a common tool for both clustering and manifold learning. The idea is you construct a Gaussian kernel, and then you compute the Laplacian, which is the computed by a matrix D minus K. And this D is the sum of rows over the matrix K. And this is one version of Laplacian. There's other versions. And then if you look at the eigenvectors and eigenvalues of this Laplacian matrix, then you can get some information about your observations X. Specifically, a lot of people use the eigenvectors of this Laplacian. That's known as spectral clustering. For clustering, that's known as spectral clustering. Or for manifold learning, that's known as Laplacian eigenmaps. I want to emphasize one property of these eigenvectors and eigenvalues, and that is that if you order them with increasing magnitude of the eigenvalues, then you're representing increasing frequencies on your manifold. So here you can see that the 0 eigenvector correspond to a DC frequency, and then a first sign, and the increasing frequencies of sine function. And why this could be used for feature selection, this was already observed in 2006 by He et al. And their idea was to use something called the Laplacian score. And that is, you take all the input features, you place them into a vector. So you have your matrix. You take columns of this matrix. Each column I'm going to call FD. And by using a normalized version of this column, that's F bar D, we can compute the Laplacian score by using this Riley-Cauchy. This is the multiplication of F transpose times the Laplacian times F from the right side. And this could be computed for all of the features for each columns individually. And the reason why this is informative is if you think of the decomposition of L to eigenvectors of I and eigenvalues, then this multiplication is no more than the weighted inner product between the eigenvectors and normalized feature vectors, which is representing the weighted correlation or squared correlation between the eigenvectors and feature vectors. So if I get a small Laplacian score, that means that the feature is highly correlated with the leading eigenvectors corresponding to the low frequency representation functions on my data. And that means that the feature is a low frequency feature. And what these authors have done is that they use this Laplacian to sort the features and then filter out, perhaps more high frequency features. Well, I think this is a very nice idea. This idea breaks once you add too many nuisance variables. So if your variables are informative, but some of them are less informative, this idea is great. But if you have nuisance variables, then your Laplacian can break and no longer represent functions on your structure. And to solve this, we've developed this idea by introducing our Gaussian gates from the previous part of the talk into all of the feature vectors. And then we construct this gated matrix X bar, which has, perhaps all the features are just multiplied by those Bernoulli random variables. And when we compute a diffusion operator, which is a variant of the Laplacian, in this variant, the actual low frequency functions correspond to large eigenvalues. And then we incorporate this into a loss, which has two parts, a regularization part, which is the same as in the supervised feature selection. This is going to impose selecting few variables, and a smoothness part, which is a sum of the Laplacian score or diffusion score for all of these selected features. The key difference here is that we're going to apply gradient descent to this thing, and the diffusion operator is going to be sparsified throughout training. So we're going to clean the Laplacian or the diffusion operator as we learn the parameters of the gates. So here is an illustration of a loss on a simple two-moons example with just nuisance variables. And you can see that the loss becomes, the black part becomes negative, and the red part, which is on the right y-axis, converges to two informative variables in this case. And this is just an illustration, but I'll show examples in the next slides. So here is this two-moons example. We have two informative features. We have nuisance variables, and then we're going to quantify the precision of our method. Again, precision in terms of identifying the informative features for different numbers of nuisance variables D. So we have several plots here on the left, and you can see that after enough epochs, we converge to a perfect feature selection in this case. On the right, I'm showing a post-selection spectral clustering algorithm that is just applied after a few epochs, and you can see that when we have the nuisance variables, the performance of the spectral clustering is bad. It's approximately 0.5. And then the classification accuracy, the clustering accuracy grows to 0 to 1 because we are selecting the informative features, because we're basically removing the noise. Then we've compared our model to other baselines for doing unsupervised feature selection. Here the procedure is you do feature selection, you select 50, 100, 150, so on till 300. You apply k-means, you average over 20 times, and you report the best clustering performance on that grid of 50 to 300. And I do the same thing for all of these models. And here I'm presenting the performance averaged over 20 runs. Again, for each model, I'm showing the best performance and corresponding selected number of features. And you can see that in a lot of these examples, we're outperforming these baselines, and we're also selecting fewer variables. In the right column, you can see that this is the clustering accuracy when you apply k-means to all of your features. So this is without doing feature selection, essentially. So you can see that there is some performance gain. There's actually performance gains for all of these, not for all, but for most of these models. Okay, so just a last comparison is between our model in standard Laplacian score. And here I selected 3 benchmark data sets, and I'm comparing for several levels of selected features. And you can see both the standard deviation and the accuracy of our model and of the Laplacian score. Oh, I forgot this one. So this is a visual example, again, for unsupervised feature selection. I'm using images for coil 20. Here I have spinning objects. So each object is captured from several orientations. And I'm adding noise to these pixels to make the problem a little bit more challenging. And I'm training our model and looking at these selected features. So you can see in the first row, the top 50 selected features, then top 100, and so on and so on. And above the images, you can see the clustering accuracy. This is a, 100 is a clustering accuracy over 100 categories. So 0.56 is not that bad in this case. And you can see that the selected features are on the axis of rotation. So they're perhaps more persistent across the different samples within each class, meaning that they're kind of more of a low frequency pixels in this example, low frequency within each category. All right, so this summarizes the talk. I'll go back to the slide I promised, but I'll just summarize. We've presented the way for doing feature selection while training a neural network simultaneously, and it relies on a new relaxation for the L0, which is based on the Gaussian distribution instead of the logistic distribution, and we observed that it works much better than the logistic distribution. And we've justified our relaxation using our probabilistic formulation from a mutual information perspective. And finally, we've presented the gate and Laplacian procedure to improve unsupervised feature selection. Okay, so this summarizes my talk, and I'll be happy to have more questions.
Good time to ask questions, everybody. Otherwise, well, for me, at first time, there was such a big audience, it was a bit hard to follow the lecture, but still, I have some questions, Ofir, that I usually like to ask in these situations. If there's none, I will ask mine. So my first question
okay, great.
is...
I'm pulling the slide simultaneously.
Okay. Yeah. Please show us that slide you mentioned if you haven't had a chance.
Yeah, continue with the question.
Yeah. So the question is, during your research, what unexpectedly difficult things did you encounter, unexpected challenges that you had to tackle?
Okay, that's a good question. There's so many, I guess. There's, first of all, when you construct a model and you train it on synthetic examples, then you really can't expect the problems of it's hard to expect the problems that come up with real examples. So I think a lot of the troubles just we learn from trial and error of working on real examples. There's things that I've learned throughout the way, which is try to think in advance about how to benchmark your method in terms of comparison. So try to select in advance which are your competitors, what are the data set that you're going to work on, and try to have a very specific systematic way to do the comparison. Because if you do different comparison across the different examples, then you're going to be killed by reviewers, and also it's better to have a systematic comparison.
Yeah, we always want to compare apples to apples.
Yeah.
You can't say one thing is better than the other if you didn't really do the same comparison process. Another question is, what did you try to do? And which didn't succeed during the research, and why didn't it succeed?
That's a good question as well. Let me try to. So there's a few things that are still open that we're still breaking our heads at, and we're not at the point that we can say what they are. So they really were not succeeding yet, and that is, we're trying to prove why is this model doing better than linear models in this really linear regression example. So we're starting to follow some procedure, but we're still failing to, have a proof of why is this model outperforming the Lasso or other models that we've compared to.
How are you thinking of tackling it?
So currently, what we're trying to do is we take these nonlinear model and we formalize the loss specifically for this nonlinear case. So basically, this loss that we have here, we plug in the mean square error loss, we plug in the model for X, we plug in the model for Y, and then we try to analyze this both empirically, to see if the loss is convex in some parts, and if it's not convex. So empirically, we do find some findings, but we have some theory, but it's not complete yet.
So you're following the old physics process. First do the experiment and then try to explain why it worked.
Yeah, exactly.
Tomer is asking, did you try or have plans to try this technique for time series models, RNNs, LSTMs?
Okay, that's a great question. I actually saw a paper online a few weeks ago that did this for dynamic feature selection, and they designed a specific way of doing this using an RNN. So this is available online. It's under review for ICLR, but it's an open. It's available online.
So I'll ask for the reference later to post.
Sure.
Any more questions from the audience? I have another question. The research team working on this, was it you and other people working on it hands-on? How many people were you, and how long did the research process take?
So we started working on this. There's a grad student, Yutaro Amada, myself and Yuval, and then Sahan joined us for the discussion and the theoretical analysis. And we had a method that was working, and at some point there was a visiting researcher at Yale that said, hey, why won't you submit this to AI Stats, which was 2 weeks from that day. And then we spent 2 weeks of killing ourselves and trying to submit this so we basically wrote the paper in two weeks. It completely failed. It's really impossible. So then we reiterated on working this, and but mostly, these machine learning venues are creating bursts of working on these sorts of problems, I guess.
Okay, my questions are over. I think nobody else has any more. So concluding remarks, Ofir, thank you again for joining here and giving this talk. By looking at the audience, by the way, everybody, we maxed at about 80 people taking Zoom and YouTube combined. First time this big amount. For me, it was a huge challenge just following where everyone is. But it also means a lot of interest, and we're still 30 people in after more than an hour and a half in the lecture. So nice job. I'm gonna send now again the links where you can find all the everything in the community. Where you will find also this recording of this lecture in the YouTube channel. All the references will be posted on the. I think Ofir disconnected. All the references. Anyways, we're finishing. Here he is.
I accidentally left. Sorry.
No worries. So we're just finishing up. So all the references will be posted on the subreddit. There is a live discussion going on the Discord channel, which is like a amplified WhatsApp for groups. The chat was also saved. If there is requests for it, we will post the chat also on the Reddit post. Sometimes we do this also. Yeah, we have more lectures coming up too, are already published on the meetup group where I think everybody here came from. One is about adversarial learning, covering 4 to 5 different papers from this year from the researchers. The other one is hydronets, is how to predict floods and alert in advance. Thank you everybody for tuning in, for joining for this lecture and for all the rest and for your participation. This is cool. Every time we're having these events, I'm enjoying it personally to see all the engagement of everybody. So thank you again.
Wait, there's 2 questions. People
go
asking,
ahead. Yeah, I didn't see.
Can you save the chat?
That's
so
so
we
that's
can,
yeah. So this and we will post it on Reddit, on the post on Reddit.
Go. Great. So is this guy that asked about correlated features still here?
I don't remember.
Yes.
Yes.
Yes,
so
I am.
You want me to show this?
I turned my camera off because it's dark here by now. I'm outside.
Sure. So I can show this slide. Forgive me that it's unorderly, but let me tell me if you can see my screen.
Yeah.
All right. So we've added 15 features, which are random linear combinations of this 5 informative features. And I'm here showing 2 things. On the left, I'm showing the precision of identifying the 20 informative features as I increase the regularization parameter. So you can see that at this point, right here, we're selecting 20 features. And once we increase lambda, we're still selecting informative features. So precision remains at 1. So we're always selecting informative features, even though we are decreasing the number of selected features. And you can see that there is a point here where the method, there's a plateau where we're selecting 5 features. So the method is actually here distinguishing between the original 5 and the correlated 5. It is actually selecting the informative 5 in this case. And in the right plot, I'm showing that if you just do cross-validation and look at the accuracy and evaluate the number of selected features, our model is a good indication of the optimal number of selected features, in the sense that the performance peaks for exactly 5 features in this case. Whereas if you use random forest, it peaks around 20 features. So this is an empirical answer, but I hope it answers your.
Why would it peak at 5? I should think that anywhere between 5 and 20 should be just as good if they're linearly correlated.
You're right,
in terms of accuracy.
You're right, but if you've identified the original 5, then your predictive power is stronger than if you selected 5 from the ones that require some linear combination to decouple the function. Does that make sense?
Well, that's a bit of a reach, isn't it? I mean, a linear network would create a combination of them, maybe nonlinear, even nonlinear combinations, and random forest would not be able to create these linear combinations, and maybe their predictive power is stronger. I mean,
yeah. So
I think the original is not necessarily stronger.
So I agree that it doesn't imply that the originals are not stronger, but regarding that the peak should be at 5. So even if you peak, one of the correlated and 4 from the informative, the peak should be at 5. right? Because you're not going to gain any more information by adding additional features.
They shouldn't lose any either.
Is the accuracy, is it the accuracy of the
Okay.
model or the
Okay. I should stress that each feature is also noisy. So the problem is not clean. So by adding these correlated feature, there are also additional additive noise to these.
So the extra 15 are somehow noisier because they're adding the original 5 noises. Like I assume that it would kind of be symmetric. So, you know, choose any 5. Well, not necessarily any 5, but you'd be able to create the original 5 from the other 15.
Yeah, but there's a slight. I think there's a slight addition, additive correlate, non-correlated. There's a slight additive noise to the variables.
Okay.
Okay, and just
so if you were to have like not noise, like add the noise after you correlate them, then it would kind of be symmetric. Like I wouldn't expect that there to be a right answer. There isn't a right answer in that case.
If you have, I agree if you have infinite samples. I'm not sure that the predictive capabilities are, you know, if I have, what you guys are saying is that if I have 2 functions, and if I have less samples than variables, then my accuracy is going to be the same if the function is more complicated or not. And I'm not, I mean.
But just as a thought experiment, let's say I have my original data, which is n by 5. And then I multiply that by some linear matrix, which is, and it just like upsamples it to 20.
Mm-hmm.
I'd be able to learn just as well from the new data as from the old data.
If it's informative, I agree. But if it's noisy, then I think you're
like I shouldn't have lost any data.
Yeah, I agree. If it's completely informative, then I agree. But I guess if it's noisy, it really depends how the noise affects the model. So yeah, if the variables are completely informative, placed on, you know, the exact dots of the hypercube, and then just linear combinations of these variables, then I agree that this should plateau, should perform exactly the same between 5 and 20. But I think here, because of the structure of the noise, we have this degradation of performance.
All right. Thanks.
Sure.
I think this is it. We already had the closing remarks. So if anybody has more questions, just post it on the Reddit and we'll take it from that textually. Thank you, everybody. Ofir, especially thank you, of course.
Thanks.
And have a good evening, good morning, depends where you're from.
All right, thanks.